Hi. Today we're going to talk about how to calculate pressure in Earth's crust. Okay, so the concept that we have here is there's some column of crust of some distance z in kilometers, and we want to know what is the pressure here. Okay, so first of all, let's think about what pressure is. Pressure is a force per unit area, and the units are in pascals. How does this break out in terms of units that we can really use? Okay, force is measured in newtons, and area, we're going to take an area of a meter squared. So a pascal is a newton per meter squared. A newton is a kilogram meter per second squared, and then divided by meter squared gives us pascals. Okay, so this gives us a sense of how we're going to go about calculating the pressure down here. The first thing we're going to do is we're going to find the mass of this column. We're going to measure by gravitational acceleration, 9.8 meters per second squared, and then we're going to divide by the area over which we're calculating our pressure. Okay, so let's make our whole situation simpler. Here, what we would really like rho in is kilograms per meter cubed, right? Then all our meters cancel out. Unfortunately, many densities are measured in grams per cubic centimeter, right? And so how do we do the conversion from grams to per cubic centimeter to kilograms per meter cubed? Turns out it's a factor of 1,000. 1 gram per cubic centimeter is 1,000 kilograms per cubic meter. If you have a cubic meter of water, it weighs a ton. If you're using the English units or American units, if you have a cubic yard of water, it weighs a ton. It's almost 2,000 pounds. Okay, so now how can we use all of this to calculate pressure? Well, we take our volume, which is going to be 1 meter by 1 meter by, what do we want to use for z? Let's do a calculation at the base of the crust. Let's say it's 35 kilometers thick. So we're going to take 3.5 times 10 to the fourth meters, 35,000 meters. That's going to be our volume. Our density, what do you want to use for density? Well, granites are about 2.7 grams per cubic centimeter. Diorites, 3.1 grams per cubic centimeter. Let's say the crust is about some composition intermediate between that. Let's take 2.9 grams per cubic centimeter. Okay, what is that? That's 2.9 times 10 to the third kilograms per meter cubed, right? 2.9 grams per cubic centimeter. Now what do we have to do? This is our volume. That's our density. So this gives us meters cubed. That cancels out here. So we're going to have kilograms. Now what do we have to do? We have to multiply by gravitational acceleration times 9.8 meters per second squared. And then we have to divide by our area. Well, what's our area? We chose an area that's 1 meter by 1 meter, and so this all gets divided by 1 meter squared. Okay, so we have a whole bunch of units here, a lot of terms. How does this all calculate out? Well, the first thing we do is multiply 3.5 times 2.9, and that turns out to be 10.15. And then we've got to multiply these out times 10 to the 7th. Then we have to multiply by 9.8. and then we have to divide by 1. So all of this, if you calculate it out, so this is 1 times 10 to the 8th. It's about 1 times 10 to the 9th. About 1 times 10 to the 9th. What are those units? Pascals. 1 times 10 to the 9th pascals. Or 1 gigapascal. That's a useful thing to remember. Okay, the pressure at the base of normal thickness crust, 35 kilometers, is about 1 gigapascal. Now, there are other ways to express units. One thing that we talk about is a bar. A bar is atmospheric pressure, and that's equal to 10 to the 5th pascals. And so then what do you get? The pressure at the base of the crust, P crust, 35 kilometers, is about 10,000 bars, which is 10 kilobars. Another useful term to remember, pressure at the base of the crust is 10 kilobars.